I think so. Yeah. Thank you very much. So good morning, everybody. First of all, me and Fabio, we are grateful to the organizers, for inviting us here and to share with you what we think is a possible breakthrough concerning Proxima Centauri. First of all, since our results are still under revision and so embargoed, we ask you not to advertise these results outside. So thank you for the comprehension about that.
Fantastic.
So Proxima is the subject of our talk. And since our results are based on the analysis of radial velocities, first of all, for those of you who are not familiar with this technique to discover, to detect and characterize exoplanets, we just have a few words about how it works somehow. So basically, so the movie, okay. Basically, you have to take, usually with high precision spectrograph, you take spectra of the star at different epochs and look for the presence of periodical shift of the spectral lines in wavelength. If such periodic variation are present, this is likely a possibility that around the star there is a companion, and through radial velocities it's possible to detect it and to especially to measure the minimum mass of the companion. So this is the technique that was used to discover a planet around Proxima Centauri in 2016 by Anglade-Escudé. And you see here the radial velocity curve of the planet. You see listed also the spectrographs that were used for the detection. In particular, that planet was a real breakthrough because of its minimum mass and because since it is a temperate planet. So our history, our interest in the Proxima starts from there. And slightly after the detection, the discovery of Proxima b, me and Fabio asked ourselves, it is possible to confirm the planet using the same data sets, but using a different tools for model the radial velocities, in particular, taking into account one main concern that is related to the stellar activity impact on radial velocities. This is now a well-known, it is well known that a stellar activity can hamper the radial velocities because it's easily can be present some signal due to the stellar activity in the data. So by applying different tools, analysis tools than the discovery paper, we found evidence for the existence of a signal modulated in the radial velocities, modulated over the rotational period of the star, which is well known and is around 85 days. So we were able to model the signal to confirm the existence of the planet. And at that time, with that data set, we could not find any other significant signal in the data. Later on, following the campaign that took to the discovery of Proxima b, new data were collected with the HARPS spectrograph, which is one of the best in the world at the moment. So you can see here in the plot, in the left plot, the time series of the HARPS data. And in particular, we highlighted a region where distinguishing the last data of the pale red dot campaign, that is the one that led to the discovery of Proxima b. And you can see the red dots data that were collected after. It is by analyzing all these data sets that with our technique that I showed you before, that something interesting came out. In particular, when we removed the signal of planet B from the data, but keeping in the data the signal of the activity, and performing periodogram frequency analysis, what you see here is a periodogram showing a peak, very significant because it is the height of the peak is well beyond the green line that is define the threshold for the very low false alarm probability, you see that a signal, almost clear signal, almost 30 days appear in the data. So this made us curious to go on with a better and more sophisticated analysis of the radial velocities. So we are placed here to show you for the first time what is for us a new candidate planet around Proxima that we by now call Proxima C, but it is only a candidate. This is very important to underline. Here you see on the left the time series of the ARPS data once we removed the stellar activity and the signal of the planet B. And you see that there is a good modulation of the data. Especially the plot on the right is much more clear in the sense that it shows the phase-folded radial velocity curve folded on the orbital period of the candidate. You see at the bottom some important numbers of our analysis showing that, in particular, the semi-amplitude of this signal is quite low. Is almost of the order, is almost equal to the signal of Proxima B. You can see here that the orbital period is long. This is equivalent almost to a bit more than 5 years. And the minimum mass that I told you can be measured from radial velocities. It is around 6 Earth masses. This means that at this level, the planet lies in the super Earth regime. And another important value that Fabio will speak about that, we'll use it later, is the orbital semi-major axis that you see here is 1.5 astronomical unit. So from this number, you can guess that this detection is quite challenging, especially because it is made by one only technique, and the orbital period of the planet is really long. So it takes time to collect more data. And the one first important point that we asked ourselves is about, can be this signal related to the activity cycle of the star? Because the activity can impact radial velocities not only with rotation modulated on the rotation of the star, but also considering the long-term activity cycles. Proxima is known to have an activity cycle 7 years longer. You see in the upper plot the photometry showing this modulation at 7 years. And when we phase-folded our radial velocities to the same period and the same 0 point, we didn't find any correlation, clear correlation between the two data sets. So in our opinion, with the data sets we have at the moment, we can exclude, most likely, almost safely, that the signal we saw in the radial velocity is not related to the activity cycle. So for us, it's a good candidate as a signal induced by a planet. The perspectives about this discovery, this detection, Fabio is going to speak about that because it opens a lot of possibilities for confirmation and characterization.
Yeah, thank you. So Mario showed how this detection is very challenging. And so we asked ourselves a lot of times, many times, is this a real planet? But what is sure is that even if this planet is a castle in the air, well, we should absolutely keep working to put even stronger foundations under it. And so what's next? How to put these stronger foundations? First of all, we need to keep observing in radial velocities, collecting more data, because as Mario said, this is a very long-term planet. But there is much more. We are fortunate enough to have Gaia up there, and Proxima Centauri is very close to us, and this planet is orbiting on a quite large orbital distance. So this means that the minimum astrometric semi-amplitude induced by the planet on Proxima will be quite large, about 170 microarc seconds. So we performed some simulations in our submitted paper, and here this plot we show the difference of the mass of the planet that we inject in a system and then the mass that we can retrieve with two different techniques. One, illustrated by the blue dots, is only astrometry, while the other one with red dots is astrometry plus radial velocities. And this, we show the mass as function of orbital inclination. And so basically, we see that we will be able, with Gaia, to detect and to measure the mass with a 5% accuracy. And this is great news for us. This will take place in a couple of years with the end-of-mission data release from Gaia. But there is much more. Potentially, this is a spectacular laboratory for direct imaging. So we estimated that actually the planet should be well below, or could be a borderline detection with current instrumentation, because the estimated contrast ratio is like at about 10 to the minus 8 or 10 to the minus 9. But the angular separation is quite large, and if we manage to observe this planet somehow, this will be the first detection of a planet discovered using radial velocities. It will be the direct imaging of the closest exoplanetary system to us, and it will be the first detection of a planet in reflected light. So these are all remarkable goals that hopefully we'll be able to accomplish with at least next generation of instruments. And even more. So after the discovery of Proxima b, there were follow-up observations, of course, also with ALMA, to understand a bit more the architecture of the system. So this work, these are plots from work by Anglada and colleagues. In 2017, they proposed that the system has many dust belts, 2 inner dust belts and then an outer one. More, there is an unknown source that source. I mean, it's something that is up there. You can see it in the plot on the right-hand side, bottom left from the central star. This is not even a detection. This is something that is there. Could be a background source, could be noise, could be the effect of some other observations. We don't know. We don't know absolutely. But then this analysis, these observations were analyzed again after 1 year by McGregor and collaborators, and they concluded that at least the dust belts can be explained in terms of flare activity of star. Proxima is a star that flares quite a lot, several times per year. So definitely more data are needed. Few words about where this planet falls in this diagram, mass versus as function of semi-major axis. So these are here in the plot. There are the planets around low-mass stars discovered with radial velocities. And Proxima c, the candidate Proxima c, is the planet with the smallest signal at this orbital distance. So this illustrates again the difficulty, the challenge that we have for this discovery. And also it makes us ask some questions about how it formed, because we know, some models tell us that super-Earths tend to form around the snow line, but Proxima c at the moment is quite distant from the snow line of Proxima, that is located at about 0.15 astronomical units. It's possible that this planet migrated from somewhere else in the system, but our estimated orbit is compatible with a circular orbit at the moment. And finally, of course, we want to ask the question, is this planet habitable? Well, not really. It's quite cold. We estimated a surface equilibrium temperature of 40 Kelvin, so not really habitable, quite distant from the habitable zone that in this plot, in this animation, is the blue stripe. And here we show how it moves in time for Proxima and for the Sun on the top. So we have many exciting perspectives and perhaps even more open questions. And so we'd like to conclude with one question for you all, for the audience. What are the implications of this possible detection for life migration? Thank you.
Hi, this is microphone check. This is René Heller. First, congratulations. I'd like to stand up and shout, yoo-hoo. This is really an amazing, amazing result. I hope it withstands scientific scrutiny over the next few months and years, I guess. So in terms of confirmation or validation, not sure how to phrase it, You said the orbital semi-major axis of your candidate is at about 1.5 AU.
Right.
Now the ALMA observations of this unknown source seem to coincide with this semi-major
exactly.
axis. Are you able from your radial velocities to move backwards in time and see if this source could coincide? First question. And second is gravitational interaction of the two planet candidates. Would they result in a shift of the, say, perihelion or whatever, so that the radial velocity signals would look different in the future compared to a single planet model for both candidates, so that you could confirm interaction of the planets?
So thank you for the question, because actually it's something that I forgot to mention in the presentation. Yeah, there is this coincidence that actually that unknown source is exactly at the same orbital distance that we estimated. And from our calculations, actually should be also in the right position. Close. This is a combination of measurements that we are trying to do. I mean, also with other instruments, but it's still a borderline detection. So that definitely we need more measurements. Also, when we measure radial velocities, we can know when the planet is in quadrature, but otherwise we don't know where it is in the sky. So it could be just a coincidence.
There is also
it's there. Yeah.
The orbital we don't know the inclination.
We don't know the orbital inclination. And then, yeah, the second point, we didn't so far make any calculations about that. But surely this is something that will be addressed in a possible follow-up when the planet when at least this paper goes through, about also planet formation and then evolution of the planetary system. It's a good point. Thank you.
Hey, this is Jay Malash. Regarding your question about interplanetary migration, one of the problems about exchange of life between planets in a low-mass star system is that in order to be in a habitable zone, they have to be very close to the star. That means the orbital velocities are high. We're talking hundreds of kilometers per second. And in order to get exchange from one planet to another, encounter velocities are similarly hundreds of kilometers per second. And so it's really straining credulity to think that you might get an intact rock from one planet to another, or even a rock from a planet ejected from the solar system.
Thank you.
Thank you very much.
This was a question for you. I mean, I'm a planet hunter, and so this was like to provoke the audience about something that actually is quite new for me, for us.
There's been a lot of press on the implications of flaring. And I wonder if you run any models of looking at the kinds of flares and the effect it would have on the equivalent of the Earth's environment, given our atmosphere, which is strongly rejecting of X-rays and ultraviolet.
Concerning this candidate, I mean, actually, you try to answer, because I didn't.
So, yeah, definitely this was one of the first arguments to say that Proxima b is not habitable. Perhaps flares, they destroyed the atmosphere if there was any. So for Proxima b, but for this candidate planet is quite distant from the star. So in principle, flare.
My question was, if Proxima b had an atmosphere like that of the Earth,
Yeah.
would the flares that you think are going on have a significant adverse effect on that planet with an atmosphere like that of the Earth?
Yeah, definitely it would have effect, and perhaps these flares, where they would even be able to stripe out completely the atmosphere from Proxima.
We know that there are probably 1 or 2 papers about this possibility about Proxima b, but actually, I think we cannot answer it directly because we were focusing on the outermost planets. So,
but yeah, there are some works on that.
I don't know too much about.
There are some works. Yeah.
Thank you for sharing this very exciting candidate planet with us. I'd like to remark on your broad question at the end and René's excellent follow-up to that on the dynamics of this system. We've learned from Kepler that the majority of planets are in multi-planet systems. Multi-planet systems, especially with very compact architectures, are a common outcome of planet formation. So when thinking about the dynamics of this system, in particular whether the radial velocities need some additional contribution, I think that could be the case. However, I don't think the additional contribution would be from, say, non-Keplerian effects, because the orbital period ratio between Proxima, Cen, B, and C is quite large. So the dynamical timescale of planet C perturbing B would be very, very long, longer than the baseline of their RVs. But my concern is that there are maybe other planets hiding in this system that we haven't found yet. In general, in any system, you don't know what planets there are that you haven't found yet until you find them. They are an unknown unknown, which makes it very challenging to accurately model and fit radial velocities. So with regards to that, one concern I have is that there are indeed additional planets in this system, but that the peak in the radial velocities you've identified is some combination from additional planets plus noise that maybe means that there are additional planets, but not at the period at which you're announcing the candidate. So I don't know really what we can do, except for, what you rightly said to do, is continue monitoring with RVs and also look for some sort of motion from Gaia. That's all we can do, is just keep working, and it's going to be a long road, and I really appreciate all the dedication and courage you've put into it.
If I can comment, yes.
And sorry, and one more comment about the person who doesn't think that there can be planetary material moving between planets because of the high velocities. That's just false. Ben over there has a Martian meteorite that landed on Earth. So you can get material moving from planet to planet as long as it's small enough material.
I just want to give a comment about the possibility of other planets in the system. This is for sure. This is something that we expect. Since we are talking about M dwarf, and especially small planets, low mass planets should be frequent in that system. The point is we are limited now, at least from the radial velocity point of view, from the precision of the measurements. And in particular, I expect in the following years, so not immediately, not in the near future, but a bit farther, a contribution from Espresso. Espresso is another spectrograph, just started operation with VLT, and it will provide a much more precise measurements of Proxima. So precision that is necessary to search for a lower mass planet than those already discovered, and even maybe to model the activity of the star in a much better way. The point of modeling activity of the star, I hope I was clear in presenting, was important in this work, because we removed at least one contribution that we even compared with photometry. It looks nice. It looks astrophysically robust. Probably it can be more than interfere. This I don't know at the moment. So I prepare for
time for one more. I don't know if you're familiar with Chris Mann and his NIAC-funded study on stellar echoing for imaging exoplanets, but he's got an approach where he intentionally uses some advanced signal processing to separate the signal of an echo off of a planet from the source star, and it's funded through phase 2. And one of the challenges that he has with making this technique work, it's a completely different way of detecting planets than the approaches that are typically used. The challenges he has is the planet has to be particularly large, particularly far from the sun, and it has to be a flaring star. And what it looks like is that you have an ideal candidate for Chris Mann's technique, which may be a nearer term way to at least detect the existence of the planet. And should there be more than one, you know, he gets extra little signals. But I don't know if you're familiar with his work. If not, we can talk. But this looks like an ideal candidate for his technique.
Great. Thank you for pointing out.
Thank you.
Very interesting. Thank you.